Log on, tune in, find out. Another good idea from Cambridge.
So I will speak about discretization of inverse problems, and as an example of this I will consider X-ray tomography. So let us consider first how I formulate measurements. So we are interested on the attenuation coefficient, for instance inside human body, and then we do X-ray measurement. So you here denote this unknown like attenuation. Then we have an X-ray measurement that is linear, corresponds linear operator A here, and then we add some noise and get this noisy sinogram. So in this kind of configuration, it's somehow it's classical result that using filtered back projection imaging we can do excellent reconstructions. But to apply this filtered back projection formula, one has to collect lots of data. Especially it is important that that one measures from all angles. And because of this, one uses lots of radiation. So in one way one could say that the reason that we have chosen the filtered back projection formula causes that we need data that causes lots of radiation for the patient. So you don't do it that easily. And in this talk we have a little bit different point of view. We somehow think that let's do very few measurements and let's try to change mathematical algorithms in such a way that we can get some measurements, so we can get data that is needed for clinical decisions. And this was our motivation when we started a project in 2001 with the Finnish company Instrumentarium Imaging that was later bought by GE Healthcare, and then later it was sold for Paludex Group. And in this moment they had three different type of devices: one for dental X-ray tomography, one for mammography, and then for surgical surgical X-ray imaging. And what they want to do, they wanted to change these devices that basically were operated very closely to the ideas where you want to use films, not digital sensors, to change the algorithms in such a way that these devices would be used with digital sensors to implement three-dimensional imaging. So what was the clinical task that they were interested in? Here is one example in dental X-ray tomography or imaging. One of the crucial problems is that when you want to make a tooth implant, then you have to drill a hole, but you want to make it deep enough so that the implant stays there, but you want to be sure that you don't damage this nerve channel here. So the doctors want to know just one measurement, in this case for instance, what is the depth that is safe to make the drilling here. And now the measurement configuration is very different for full angle CT. There is measurements only for 40 degrees. So here is the jaw of the patient, and behind the head one measures with X-ray sources, takes this type of pictures, and here the medical doctor would like to see nerve channel that is go somewhere here and measure distances. So this leads to a limited angle X-ray tomography problem. So to understand this, we study. We started with this kind of like simple examples where you somehow take just a single tooth and measure it from different. You basically turn the tooth to take actually a full, like this kind of like full X-ray transform, the full CT, but then you somehow forget most of the data and want to do reconstructions. So here are the X-ray pictures, and that represents like the full CT data. Then we forget we take only 60 degrees of data, forget most of the pictures, and want to do measurements. And how we do this reconstruction? We used Bayesian approach, so let me shortly recall the basic methods. So we have random variable u here, that is like the attenuation. Then we have a linear operator a. We add noise and get a measurement. And I use these notations throughout the talk. And in Bayesian paradigm, one assumes that one knows so-called a priori distribution for the unknown u. So one has some idea how u looks like before any measurements. Then one assumes that one knows the measurement operator a, and this noise statistics. Statistics of noise is also assumed to be given. And in this talk, I will later analyze the question: what happens when one makes better and better discretization? So when dimensions here of this problem approach to infinity. In Bayesian tomography, there's a big, long history, starting from important papers of Hansen, but they are like very extensive work. This is only for X-ray tomography, and there is a vast literature for PET and SPECT imaging. So let me just recall the Bayesian method. I denote here this pi u of u. This is for the unknown u, the probability density function evaluated at value u. Here I have conditional probability density functions. And Bayesian inversion is very convenient for inverse problems, because if you want to compute the conditional probability, actually density function, that the unknown has value u, assuming that we know the measurement m, Bayes formula has here same quantity where we have changed the object and the measurement. So here we have likelihood function that assume that we know what the object is, what is the measurement. We multiply it with a priori distribution and divide it by some number that we consider as a constant, because it depends on the measurements we do. And if the statistics of the noise is given, this is the formula that we get here. So basically, this here is the solution. This function is the solution, Bayesian solution of the inverse problem. So how this is in practice? In practice, this kind of function is not enough. We want to have concrete estimates. There are two important estimates we are interested in: the conditional mean estimate, that is the average of the posterior distribution, and then the other is maximum a posteriori estimate, that is closely related to maximal likelihood estimates. So this is the like a median of the posterior distribution. Largest value, the value u, where this probability that of the object has value u, assuming that we have measurements m, that this quantity is maximal. And we are also interested on confidence intervals to quantify uncertainty. So how this looks in practice? Let's look at this X-ray tomography problem. We discretize it. So this is the example of what I mean by discretization. In very, very simple case, we have the unknown object. We decompose it to pixels. Measurement is basically summing with some weights these pixels, and this is our measurement data. And this type of in the X-ray tomography, here I have source, rays go like this. I have detector here, and I have pixelization of the unknown. Okay, so actually, so this is now our model. U here is a vector where I have attenuation on each these pixels. So what type of approach we used? For these pixel values, we chose the total variation prior, or discrete total variation prior, which means that the a priori probability for values u is e to power minus some constant alpha times the sum of total variation of the picture. So let me go back to the last slide. Here I have these pixel values. I look neighboring pixels, and I put here this type of penalty function where I have absolute value of neighboring pictures. So I minimize basically this. So this kind of thing is small if the neighboring pixels have close by values. If we have Gaussian noise in the measurement, then the posterior probability density function here is product of Gaussian function and this a priori density function. And if I just look to maximum a posteriori estimate, this is equivalent to this type of total variation regularization, or developed by Rudin, Osher, and Fatemi. So this map estimate now is the same as Rudin, Osher, Fatemi estimate. The other estimate we are interested in is that we take this function, put it in here, and compute the conditional mean estimate, the average of the posterior distribution. And Bayesian approach is very flexible in the sense that it is easy to somehow put here modifications for the prior. For instance, add the data that all attenuation values are positive. So I just put here characteristic function that all pixel values are positive. And this is actually how we did these pictures. So let's look at the pictures. Here, the picture was now, this was our data here. From this configuration, this was our data, and we are looking now this kind of slides, horizontal slides in this picture. So here was somehow we used the all data and filtered back projection to get something that we can consider as the truth, how the cross-section looks like. Here is the traditional method, that was just a non-filtered back projection. And it looks like that. And these total variation pictures look like this. Like you see, this picture is prolongated to one direction. What is the reason for this? It is known that one can see only some parts of the singularities. Actually, the results by Greenleaf and Ullman, and later also discussed by Quinto, and concrete estimates by Ram and Katsevich, they explain that if we have here X-ray sources and our detector is here, then we have some singularities or jumps are visible and some are not. And the prolongation of picture is in this direction. And in medical imaging, one is interested in detecting these jumps. And these techniques of Greenleaf and Ullman were based on microlocal techniques, general microlocal techniques developed by Guillemin and others. Okay, so these were the pictures I showed you a few slides ago, these horizontal slides. Medical doctors don't look ever this type of pictures. Like you see, these are not, they don't look very good. So let's take all of these type of two-dimensional pictures and let's put them on top of each other and take a vertical slice. The vertical slices look much better. So here is this this kind of basically like full angle CT, the truth. Here is this kind of non-filtered back projection reconstruction, and here is the total variation reconstruction. And here we somehow some structures here can be seen quite well. So these kind of things we did during 2001, 2003. And here are somehow more clinical pictures. You put the intraoral like detector in the mouth of a patient. You take angle 60-degree like limited angle data. This is the traditional non-filtered back projection, and this is the total variation reconstructions using the maximum a posteriori estimates. So the details in vertical slices are much more visible here. But we are not only interested on maximum a posteriori estimates, also on CM estimates, so conditional mean estimates. One reason for this is that if you somehow compare these estimates, you see that this prolongation here in CM estimate seems to be less, a little bit less than in this picture. And also in statistics, people are very interested on the conditional mean. Also, using Bayesian methods, we can also not only somehow compute the estimate, but we can also look confidence intervals. For instance, in this picture, here is somehow one slice of the tooth. We can take here a pixel number of 16,400 something, and look at how confident we are that the value is like this here. So in principle, we can somehow say that how sure we are that reconstruction at this point is what the picture shows like. And this type of uncertainty, qualification of that, is important. And this, I want to recall, it wasn't this pixel 1600 something. Why I want to somehow emphasize this? The reason is now that we have now discretization that we have put there ourselves. The nature doesn't give us any particular somehow or preferable discretization. So actually our physical model, at least how we think nature, is that we have functions in three-dimensional space. Then we discretize the measurement by putting here detectors. So the detector size might give a natural discretization for the data. But in the object here, you could have put one discretization on another, or even somehow denser ones. You could put here better detectors, or even make more measurements. And when we think this somehow these changes of discretization here inside the domain, our algorithms should work well with all possible discretizations. This X-ray tomography was, I would say, too difficult example for us to analyze in very well. Okay, sorry. First, few comments about, so when we let this n and g go to infinity, this is infinite dimensional Bayesian analysis. And there's many papers on this. In particular, Mandelbaum studied this in Hilbert spaces. Then in Finland we have a big school studying this. The seminal paper for this was the paper of Lehtinen, Päivärinta, and Sommensalo, where white noise was first time considered as like random distribution. This kind of technique were later generalized by Fitzpatrick to Banach spaces, and there are like in Finland, Latsanen and Piironen have studied systematically this kind of estimates in infinite dimensional Bayesian analysis. And I would like to also point out a paper of Helin and myself, where the Mumford-Schach reconstruction has a Bayesian interpretation. So like I said, this kind of models are very difficult to analyze systematically. So let's go look very simple, like toy problem. Let's look one-dimensional case. I draw here a picture. Like this, we have interval from 0 to 1. I divide it to n points, and then I consider that I have here piecewise linear function. At each somehow point here, like 3 over n, it has value v3. And then I consider this total variation prior. I take the neighboring values, sum them together, multiply with a constant that is almost like regularization parameter, and compute the exponent of that. Then I consider a measurement that is that I evaluate this function in some points, for instance, here and here. And then I analyze what happens when I increase the discretization. So this n, when I divide the interval to n subintervals, what happens when I increase the number of n? And one would think that maybe this approaches to this type of object. Like I wrote here just a formal, this kind of formula that I don't know if it means anything. This kind of probability distribution that I would have the total variation of the function multiplied with constant and put e to power that. And we were very hopeful first that this would be somehow a good idea, but this doesn't mean, it seems that for me now that this doesn't mean anything. Why is that? Okay, so here we have these parameters alpha n. And if we like to somehow choose them in systematic way, then I increase number n. Okay. What happens if we choose with Samuli Siltanen, we obtain following results, which somehow says that this kind of total variation prior is not discretization invariant. And what it means? With different choices, so there are two somehow good choices when you get some kind of convergence. One is that this parameters here, actually we have this parameter minus alpha. This alpha is constant. Then the maximum a posteriori estimates converge to this this total variation regularization problem or Rudin-Osher-Fatemi problem. But when we look at probability distributions, they don't converge at all. So there's no limit distribution. If we want the probability distributions to converge, so that this would have a sense in sense of like stochastic statistics, we have to choose alpha n to be n to power 1/2. This is due to the central limit theorem. Then the probability distributions and CM, the conditional mean estimates converge, but the limit is Gaussian. So it's very different. Here we don't have a Gaussian, we don't have quadratic function. So if I put here power 2, I lose the edge preserving properties of this type of regularization. And in this case, the maximum a posteriori estimates converge to 0. Let me show this. We have recent numerical simulations with Kolehmainen, Niemen, Nimäki, and Siltanen. Let me show how what we did. So we have this type of one-dimensional problem, and then we compute a convolution of it, like here. I use actually torus, so I actually periodic functions to remove somehow difficulties near the boundary. So I take the convolution, I evaluate the convolution at some points and add some small noise. And this is our data. These blue dots are the data that we use as given data. Then we do reconstructions. Here is first Gaussian reconstruction. I use Gaussian a priori distribution. That is the same as here. I would put here actually power 2. So that is the Tikhonov regularization. The solution is quite somehow smooth. These edges are smoothened away. How about total variation? So here I have this maximum a posteriori and conditional mean estimates. Discretization is 64, and now I increase it. Let's look what happens. These maximum a posteriori estimates, they are edgy. They seem to converge quite nicely, but the conditional mean estimate, this blue curve here, starts to oscillate, so this shows that how it doesn't converge. So this was for the choice when alpha n's were constant. Let's look with different choice of these parameters alphas here. What happens? Here is again the same picture, and let me go increase discretization. You see this goes down. So this somehow shows here how the map estimate starts to go to 0, and the CM estimate converges, but it converges close to Gaussian limit. So this is what we call the discretization dilemma. of total variation prior. Here are the results. Here are alpha parameters is fixed. Here alphas are square root of n. I look CMN map estimates. And the summary is that so with fixed parameter, the maximum a posteriori estimates converge, but the probability distributions diverge. With this choice of parameters, the probability distributions converge, but the reconstruction becomes smooth. The CM reconstruction becomes smooth, and here the map estimate converges to 0. So this shows that the discretization of priors and this kind of computational problems in Bayesian sense has some difficulties. Because of this, we started to somehow study this more systematically. And let me first somehow define some concepts so that we can formulate the results. Now we think that we have some random variables in some function spaces. So we have actually a torus, d-dimensional torus, and I look for some function spaces. They are usually Sobolev spaces or Bezoar spaces. So they are subsets of distributions on this d-dimensional torus. So I assume that this unknown that I want to find out, this u, that is some Banach space that I denote by b. This operator A is linear and it maps Banach space B to Hilbert space H. And in this Hilbert space, I have some Gaussian random noise. And to have computation solutions, we need to discretize this problem. And we say that this kind of discretization is good. So we have discretization invariance. If we can use any kind of discretization of these objects as actually arbitrarily find discretizations for these objects, and we have some convergence of solutions. Now there are three different types of models. First is that we call the continuum model. In CT, this would be the same thing that I have really a physical body. I have here this kind of plane where I measure the radiation coming from this point. All objects are here functions in continuous space. Then we have practical measurement model, where I put here a detector having k pixels. So this is the configuration where we get our data. We have a real human being. We take images of that, of him or her, and have a sensor that is discrete and give us finite collection of numbers. Then we go to computer and we discretize it. This model is now discrete. Everything is here discrete. So here are the recall of this in the general case. We assume that I have a projector pk and projector qn. We have this continuum model where nothing is discretized. Then we have practical measurement model where I have discretized the measurement. I operate with the projector pk. Sorry, here should be tn, not qn. So I have to change the notation here. And then I have for numerical solutions, we have computational model where everything is discretized. The model looks like this. And I have here a finite dimensional random variable which distribution is the same as projection of u. So here I recall just things from the previous slides. My measurement is this, that I have basically continuum measurement, and then I have measured it with device having a finite number of pixels. And the data is a realization. So these are all random variables. Measurement is realization of the random variable measurement mk at the element of probability space. Now there is a surprising technical difficulty. It is that the data that we use when we somehow have real data, in simulations the situation is different, but when we have real data, the measurement is related to this practical measurement model. But we do all computational work using this computational model. So we need to answer the question that what means the conditional expectation for this discretized variable in the computational model, assuming that the measurement comes from the practical measurement model. The problem is now that this object is in this computational model, and this object is in this different model. So what is the difficulty here? We would like to define this something that it would be the projection of the like the continuous reconstruction. But this kind of object, it is not determined by our computational model. Namely, the distribution of discretized variable, discretized noise, and discretized measurement operator, it does not determine this. So why this is a problem? When we somehow want to compute CM estimates, how we do it? We do all model computations in this fully discretized model. For instance, usually we use this type of like Monte Carlo Markov chain reconstructions. We take the computational model and take samples from it with different methods, compute the average, and this is our reconstruction. So, but it is not, because everything is determined by our computational model, it cannot be this. So this is why we made a definition. We defined the concept of reconstructor. It's actually a very fancy name for a very simple thing that we are all familiar with. So the reconstructor actually is the practical algorithm that we use to solve the problem. We have the computer program, we can put there anything and it gives the answer. And if it works well, if the solution is somehow reasonable, that it solves the problem correctly, then we call it reconstructor. So we say actually that this kind of reconstructor related to measurement m, unknown u, and measurement m, it's a deterministic function where we map measurement to this function. If this function coincides with the conditional mean estimate in the case when this measurement m is the realization of the measurement. So here is the rigorous definition in terms of conditional probabilities. The reconstructor is the conditional probability of the unknown u if you put there the realization of the measurement. Why we define this? We had this problem that our data came from different model that we analyze in the computational case. Now we have this kind of deterministic function. So we have this kind of reconstructor related to the computational model. It is just determined by the computational model. And we can put there anything we want. Especially we can take the realization of the measurement coming from very different models. And here is the result that we proved with Saxman and Siltanen, that if this kind of condition, we say that the exponential moments of the a priori density are finite, then if the discretization operators, these projectors Tn and Bn, converge in suitable way to identity operators, and if the measurements, discrete measurements converge to continuous measurements, then the reconstructors converge. So this basically means that the solutions obtained by the computational models, they converge to the solution related to the continuum model. In particular, this type of cases, this limit is true if we take this kind of continuum measurement, like X-ray somehow radiation, and we put there sensors that detect it with k pixels, and number of k goes to infinity. So this is pretty abstract. Let's now go back to very somehow concrete case. Let's go back to this total variation example that we had here. So I recall that we had the problems that the probability density functions, the distributions, didn't have any sense when n goes to infinity for total variation priors. So let's modify It's just slightly. I use this type of, let me write here, I have this e to power minus alpha u, and now I use total variation. I just write it like gradient and L1 norm. I was define this kind of frequency band filters Kj. So they are like Littlewood Bailey projectors. I take Fourier space, I put their dyadic decomposition. So these are getting larger and larger. And then I somehow make a filter that takes this Fourier, somehow this frequency band in two-dimensional case. Now here I have the total variation prior that makes no sense. But let's look separately all frequency bands. I put here this frequency filter for frequencies 2 to j to 2 to j plus 1 and sum them over. Now this makes sense. So actually I use total variation prior in all this kind of frequency bands separately. And the idea is that this is a Bezow space norm. This norm is actually equivalent to Bezow space, and there I have indices 1, 1, 1. And that's very nice space because wavelets are their basis. In particular, in two-dimensional case, the wavelet coefficients, their L1 norm is equal to the Bezow norm of this function. And because of this, we now think that this is quite close to Bezow total variation. We have total variation, but all frequency bands separately. Now we define here the Bezow prior, that is like analog of total variation prior. And this is well defined. And we can show that the reconstructors, basically these kind of computational mean estimates in the discretized models, they converge to the continuous model in suitable Bezow space, and it is very somehow explicit error estimates. So this happens for the CM estimates. For map estimates, like I said, this norm is very close to L1 norm, and we are using wavelets. So these map estimates, they are equivalent to this type of L1 regularized solutions studied by Daubechier, De Vries and De Mol. And also I note that there is very somehow sophisticated error analysis in terms of regularization theory, that when the noise level is assumed to be known and when it goes to 0, is the typical setting in regularization theory, then Grasmeier, Haltmeier and Scherzel have studied the properties of the convergence of this type of map estimates, or actually the regularized solutions. So by using this type of technologies, one can apply them for this kind of this Bezow 1, 1, 1 priors, and see that not only like when error levels goes to 0, but also when we increase the discretization, then the solutions converge to this one, this minimization problem. Here we have basically L1 norm. So now this is very interesting. For this Bezow priors here, alpha n's can be chosen constant, and then both the CM estimates and map estimates converge. And let me show also numerical simulations with the same group as before. So what I recall what we did. We used wavelets. So here is actually we use this finite wavelet projectors. We take n first. Actually, we take 2 power capital N first wavelet coefficients. Using these wavelet coefficients, we define first the Bezow norm. We just weighted L1 norm, and then we have these Bezow priors. And this we use the prior to compute conditional mean estimates and map estimates. And here are the results. So here is discretization 64, wavelet coefficients used. Then I increase it. Let's look here. By chance, map estimate and CM estimates are in top of each other. So they are the same curve. Now I increase discretization. Now they converge very nicely. And it was somehow very surprising for us. We don't know yet what is the reason. It is that CM estimate and map estimates for this convolution example, at least to this discretization, they are visually the same. This is very interesting because map estimates are very easy to compute. CM estimates give lots of information about the distribution. Just like average gives lots of information about the distribution. And we don't know yet the reason why they are so close. The implementation where these are computed are quite different. So that shouldn't be just like computational. That shouldn't be an inverse gram. Okay, so let me go back to medical imaging. Actually, we use this type of Bezoar priors or based on wavelets. Before we had this theory, we were applying them for mammography. And also now by using Bayesian analysis, so-called empirical methods in Bayesian analysis, one can estimate that what would be the parameters. We had, this is like Bezoar 111 prior. The parameters will be now changed. They fit better to the data. And in MammoX, this is like this kind of phantom modeling breast tissue. Actually, this, I don't want to go into detail what it is. But I mean, this is somehow like phantom, physical phantom modeling mammography measurements. So here we can see this kind of details much more clearer than in back projection reconstructions. Also, then I have few slides from Samuli Siltanen's talks, where he somehow was analyzing data in measuring this jawbone. So I think. So here, our comparison of lambda tomography with all angles, but with only with rays that go through the region of interest. And here are Bezoar reconstructions, so they are much somehow better. These are map estimates. And also, if one does modeling, that one does outside this region very coarse modeling, and here fine, then it seems that it's enough to do fine modeling inside this region of interest. So this is actually this Samuli Siltanen, S is here Siltanen, his paper. Unfortunately, we don't yet have, for Bezoar estimates in real data related to medical tomography, we don't yet have CM estimates. So I emphasize that these are map estimates, but I hope that CM estimates would look similar. Thank you very much.
Even from limited data, you still know a convex set that contains the support of the function. So you know that there are regions outside your tooth or whatever that are zero, and yet you've reconstructed something there. Wouldn't it be better just to constrain the reconstruction to be zero outside the convex set, the convex set that contains the support?
I think this actually yes. So this total variation reconstruction, for instance, that I showed, I mean, those had the positivity prior. So they basically take care about this. That in this limited, so we here where they have a tooth, then we have 40 angle degree. We know that. So you are speaking about this convex set here. And now when we have the positivity prior, when we know here that the rays give zero, then automatically the solution is zero here. So that positivity prior maybe takes care about this issue.
So why do your reconstructions have stuff outside the?
So this. I think that in this picture, in physical measurement, I mean, this is something that you don't have. You have the attenuation is non-zero in this area. It's just that here you use so coarse like modeling that you don't somehow see it. This is like, and you somehow in this reconstruction you use an arrays that go through this radiation of interest. So all details here, even though there are some, are not visible in this reconstruction.
So did you compare this one with the TV, just using TV? So you're using this. Is it very different?
Yes, it is. As far as I understand, they are quite similar. Yes, we wanted to study this bezo prior because we know that, that now that, so this is the thing that total variation is not discretization invariant. It means that there's a big danger that when you choose this parameter alpha, so that in your test pictures it looks good, you somehow choose parameters in your codes in such a way that it works well in your test cases. But if you somehow change the discretization, it might be that this parameter is very different.
Also, if the prior is using, regularization is using the standard Tikhonov, will this dilemma still exist? Or the dilemma?
So for Tikhonov regularization, let me go back here. So for this Tikhonov regularization, things works fine. It is just that the total variation has no probabilistic interpretation.
Okay, maybe we should move the discussion to the coffee right next door. Okay, and we will be back here at 11 o'clock.